This continues the lectures on Galilean relativity, specifically two-dimensional cases where the vector triangle that is formed by the velocity transform is not a right triangle. When you don't form a right triangle with the velocity vectors, then the easiest way to analyze the problem is to break the vectors into their components and then add them together by using the velocity transform. So we're going to take a look at two examples in order to illustrate. The two examples are very similar to each other. Go ahead and access the first example now while I read it to you. A plane has an airspeed of 300 kilometers per hour and is pointed due north. If the 50 kilometer per hour wind is blowing 10 degrees south of west, what is the plane's ground speed and direction of travel? So I'm using here some terms that are common to aviation in addressing this example. However, before we address those terms, let's go ahead and define things. Okay, so we're going to be using once again the velocity transform like so. And then the stationary reference frame, as it always is the ground. Okay, think of this problem as being analogous to an earlier example involving a boat in a current of water. Think of the current in this case as the wind, and the object then therefore, of course, is the plane. So O prime, the moving reference frame, analogous to a current of water, is the wind, and then the object is the plane. Okay, and then it says that the plane has an airspeed. The word airspeed is a term that is used in aviation, and it specifically refers to the speed of the plane, the object, with respect to the air, the wind, which is the moving reference frame O prime. So what we're given is the magnitude of the V prime vector. The V prime vector's magnitude is 300 kilometers per hour. Okay, and then it says that the plane is pointed due north. The plane's nose is pointed due north. This is also referred to as its heading. Now, on a simple diagram such as this, north, south, east, west is defined in the following way. So then therefore, if the plane's heading is due north like so, this then means that on my two-dimensional diagram, the plane is pointed in this direction. However, due to the wind, does the plane actually move that direction relative to the ground? No. So then therefore, if the plane's nose is pointed due north, what that is the direction of the velocity vector V prime. It's describing the velocity of the plane relative to the air. So relative to the air, the V prime vector, the velocity of the plane relative to the air, looks like this. And now because this is not going to be a right triangle situation, let me go ahead and immediately write this down in component form. The vector V prime is equal to 300 j hat kilometers per hour. Okay, and then we have the wind. The wind, by the way, is always being described with respect to the ground, not with respect to the plane. So then therefore, if we're given the details in the second sentence of the problem of the velocity of the wind relative to the ground, all of that is the velocity vector U. It's describing the velocity of the wind relative to the ground. Okay, we're given its magnitude as 50 kilometers per hour. So U in magnitude is 50 kilometers per hour. And then it says that the wind is blowing 10 degrees south of west. It's blowing in that direction. Now, 10 degrees south of west is as follows. This is the westerly direction, and then 10 degrees south of it looks like this. So the vector U then therefore points into the third quadrant on the diagram. Let's go ahead and draw it out. Okay, so right here is the U vector like so, and then with respect to the positive x-axis, we're actually given this angle right here. This angle right here is 180 plus 10. It's equal to 190 degrees. I'm going to take cosine and sine of this angle here in order to describe the components of the U vector like so. And now in component form, we're then going to have the following. Here's the adjacent side of the triangle, which is equal to the hypotenuse multiplied by the cosine of the angle. And then right here is the opposite side of the triangle, which is equal to the hypotenuse multiplied by the sine of the angle. So, as I previously have mentioned in a prior lecture, always define the angle with respect to the positive x-axis. Because if you do, and then just take cosine and sine of that angle, then all of the negative signs are going to take care of themselves. I'll do that in a few minutes when I add up the vectors themselves. Okay, now speaking of adding up the vectors, what then happens in this situation? How can we picture the vector triangle associated with the velocity transform? Well, imagine that the plane's nose is pointed like so, and then we have a headwind that's blowing in this direction. So then therefore, relative to the ground, the plane is going to end up moving, say, something like this. If you can then picture that, this then allows you to draw out the vector triangle. That then looks like this. So v prime, that is the velocity of the plane with respect to the wind, plus u, the velocity of the wind with respect to the ground. That then equals our unknown, the velocity vector v. This right here is the velocity of the plane relative to the ground. So v prime plus u is equal to v like so. Okay, now here is our unknown vector v. Let's go ahead and draw it off to the side, like this. Okay, there's two things about this vector that we don't know. We don't know its magnitude. The magnitude is typically referred to as the ground speed. It's the speed of the plane with respect to the ground. Nor do we know its direction. There is some angle here, theta, associated with this vector like so, where we then have components to the vector here and here. So then therefore, once we've solved for that vector v in component form, then we'll use a little bit of basic trig in order to find its magnitude and its direction. So we'll keep this in mind in just a few moments. Okay, now how do I write out the solution to this problem? Well, all that we do is now plug everything in directly into the velocity transformation equation. Right here is our unknown, the velocity of the plane with respect to the ground. This then equals, first of all, v prime, which is right here in component form, 300 j hat, plus u, which is right here in component form. So plus 50 cosine 190 I hat plus 50 sine 190 j hat. And now we just add up all of the I hat components and we add up the j hat components and now get the velocity vector v in component form. So once you get to this point, then the remainder of the example is pretty straightforward. Okay, first of all, let's do the I hat component, which is right here. And now watch the negative signs take care of themselves. So 50 times cosine of 190, and this works out to be about negative 49.2. Like so. So that negative 49.2 is describing this component here of the velocity vector v. Notice that it does point to the left-hand side, hence the negative sign. Okay, now let's go ahead and add up the j hat components. So I first of all have here 300, and then plus 50 times the sine of 190 like so, adding all of this up, and it ends up to be about a positive 291.3. J hat, all in terms of kilometers per hour. So right here on the diagram is the 291.3. Notice that we have a negative x component and a positive y component, so the velocity vector v points into the second quadrant as we intuitively guessed earlier in the example. Now this right here is the velocity of the plane with respect to the ground. However, in aviation, we always do things in terms of magnitude and direction. So let's go ahead and find the magnitude of this vector by doing some Pythagorean theorem. Keep in mind that this side of the triangle is 49.2 kilometers per hour, and this side of the triangle is 291.3 kilometers per hour. So if I just do some Pythagorean theorem, let's see what we get. I should, by the way, get something less than the airspeed of 300 kilometers per hour because we have a slight headwind in this problem. All right, so 49.2 squared plus then 300 squared, or 291.3 squared, excuse me. 291.3 squared, there we go. And then take the square root of all of that. And that comes out to be about 295.4 kilometers per hour. This is the plane's ground speed, and as we've indicated, it's a little bit less than the airspeed because of the slight headwind. And now let's go ahead and find this direction. We'll do so by doing some inverse tangent, but we do have to be careful here with respect to which quadrant on the diagram the v vector points. So let's set up a tangent. Tangent of theta is equal to the opposite side right here of 291.3 divided by the adjacent side right here of negative 49.2. And now I'll do inverse tangent here on my calculator, and let's see what we get. So inverse tangent then of 291.3 and then divided by negative 49.2. And here's what pops up on my calculator display. Negative 80 degrees. Now I could use the 80-degree angle as long as I identify it correctly. What is the 80-degree angle that we just calculated? It's actually this angle right here. This angle here is 80 degrees. So then therefore I can leave the answer as 80 degrees as long as I write the direction correctly. Notice that it's 80 degrees north of west. Like so, as the answer. Let me double check this, by the way. Yeah, okay, that's correct. Negative 80 degrees. So 80 degrees north of west. Now, alternatively, you could also describe the angle with respect to north, like so in this direction, as 10 degrees. In this case, this would be 10 degrees west of north. Either way of stating the angle is perfectly acceptable. Okay, now picture this example in a realistic situation. In a realistic situation, it's not two-dimensional, it's three-dimensional. In addition to north, south, east, and west, there's up and down. And then in addition to that, there are accelerations. The plane is changing direction and it's also changing speed as it flies, it accelerates, and the wind is also slightly changing speed and direction in real time. Does all of this have to be taken into account when navigating from one airport to another? Absolutely. If it wasn't taken into account, I wouldn't get on the plane. Okay, now a problem like this does require a little bit of practice. So then therefore, let me go ahead and complete a second example, which is similar to the example that we just did here. It's just with the numbers scrambled around a little bit. It's going to be, once again, an aviation problem involving a plane. Okay, let me do some erasing, however, first. Now I'm going to leave this basic description right here of this earlier example because for this last example it's going to be a very similar setup. Okay, I need to move my file. Okay, so here is that problem. A plane's heading is due west with an airspeed of 600 kilometers per hour. So right off the bat, we're given the v prime vector once again. This is describing the velocity of the plane with respect to the wind. So right here is v prime pointed to the west. This is negative 600 kilometers per hour I hat. So negative 600 I hat, there we go, kilometers per hour. Okay, and then it says the wind is blowing such that the plane moves 2 degrees north of west with a ground speed of 595 kilometers per hour. What we're given in this case is the velocity of the plane relative to the ground. That's the v vector. So the velocity of the plane relative to the ground is 2 degrees north of west, like so. It points into the second quadrant on the diagram. So right here is that vector. Like so. This is the velocity of the plane relative to the ground. Okay, now its magnitude is given to us. That's the ground speed. It is 595 kilometers per hour. And then we're given the following direction. It says 2 degrees north of west. So then therefore, with respect to the positive x-axis, this angle right here is 178 degrees. I'm going to use cosine and sine of that angle in order to describe the components here of this velocity vector v. So the velocity vector v is going to be hypotenuse times cosine I hat plus hypotenuse times sine j hat kilometers per hour. So as I work my way through the example, I'm taking the two vectors that are given and I immediately start writing them in component form. Okay, and then the unknown in all of this is the wind speed and direction. That's the velocity vector u. So then therefore, how can we begin to picture the triangle? Well, the plane is pointed like that with an airspeed of 600 kilometers per hour. However, it ends up going like this at a lesser speed of 595 kilometers per hour. So then therefore, we probably have a slight headwind where the plane is pointed like so, and the wind kind of blows like that. It blows like that, such that the plane then ends up moving like this relative to the shore, or relative to the ground. Okay, now this is just kind of an intuitive guess on my part, but ultimately we'll see if I'm correct in terms of my assumption here when we work our way through the math. Okay, now let's picture the triangle. So how do we do so? Well, we have here v prime, that's from the top board, and then here's my guess. I'm going to guess that the wind looks something like this. That's the velocity vector u, and then right here is the velocity of the plane relative to the ground. Right there is v. So you then add the vectors together in the following way. That is, you have v prime plus u is equal to v like so. And now we just plug everything into the velocity transform and solve for the unknown, which in this case is u. So first of all, we have right here the velocity of the plane relative to the ground. That's this vector here. So 595 cosine 178 I hat plus 595, let's neaten this up a little bit, sine of 178 j hat. Okay, that then equals v prime, which is right here, negative 600 I hat. And then plus the unknown, which is the velocity vector u, that's the velocity of the wind relative to the ground. So now just solve for u. So when I solve for u, I'm going to add this 600 I hat to the other side. So I have right here 595 cosine 178 and then plus 600. All right, so 595 times cosine of 178 plus 600. And in terms of the I hat components, I end up with only about 5.4 or so I hat, like this. Notice it's positive. So my guess here about the u vector pointing into the first quadrant is probably correct. Okay, now I'll do the j hat component. In order to do the j hat component, we just have right here 595 sine of 178. All right, so 595 times sine of 178, punching that out, and that comes out to be positive 20.8, give or take, j hat, kilometers per hour. So I do have a positive x component and a positive y component to the u vector. My guess that it's into the first quadrant is in fact correct. Okay, now here is the u vector itself, like so. It has a magnitude, and then there's an angle associated with it. I'll call the angle phi here to give it a different name, like so. And then once again in aviation, we always find magnitude and direction. So right here is 5.4 kilometers per hour. Right here is 20.8 kilometers per hour. And now I do Pythagorean theorem here to find the wind speed. Okay, so 5.4 squared plus 20.8 squared, take the square root of that. That comes out to be about 21.5 or so kilometers per hour. That's the speed of the wind relative to the ground. And then we'll use a little bit of tangent here to find the angle. Okay, this is first quadrant, so this is rather straightforward. So tangent of phi is going to be 20.8 and then divided by 5.4. Okay, so inverse tangent then of 20.8 divided by 5.4, and that works out to be an angle phi of about 75 degrees. And then I would have to write this as 75 degrees north of east. Once again, this right here is the easterly direction, and then the wind vector points like so. It points then towards the north of east direction, like that, okay? Okay, this concludes this lecture on Galilean relativity. This also concludes this unit on vectors and kinematics.